Hello and welcome to the Explorer Lab, your ad-free, demonetized channel at the frontier of science. We are welcoming today Dr. Matthew Szydagis. Did I just butcher your name, by the way?
No, you were very close. Szydagis. It's Polish.
Szydagis. Polish, okay. Szydagis, Associate Professor of Physics at the State University of New York at Albany. He first wrote his thesis for Chicago University about bubble chambers. I loved the name of the thesis, so I jumped on it. He researches experimental astroparticle physics, in particular direct detection of dark matter and detector development for rare events. He created the NEST software package, and he's currently involved in the LUX and LUX Zeppelin experiments. He's also involved in UAP research, but that will not be the subject of today's talk. His scientific research team, UAPX, presented their preliminary results just 2 weeks ago at the SCU conference, and I would suggest anyone wishing to know more about this to get in touch with the Scientific Coalition for UAP Study. Instead, I think it will be much more appropriate to talk about science, knowledge, and discovery. Welcome, Matthew.
Thank you. I'm so happy to be here. All right. So thank you so much for your invitation, Baptiste. And I'm going to be telling you the story of dark matter today. And even though you said, obviously, my primary topic is not UAPs today, nevertheless, I will touch upon them at least a little bit. You know, I've got to, since it's also something that I spend so much time on right now. That is a controversial topic, though, so I put on the disclaimer that these are my, personal presentation, and that I'm not representing either the LZ or Lux collaborations today, because of course, there's still a stigma on that topic.
Mm-hmm.
But I wanted to start out by telling your audience how I got interested in science, and it was really through fiction, through science fiction, particularly Star Trek Next Generation when I was in elementary school. And when I was in high school and secondary school, it was Star Trek Voyager. And really, that's what really helped me get interested in science, as did reading these books, which I read in 4th, 5th, and 6th grade. The God Particle by Leon. Oh, hold on. There we go. I accidentally exited the presentation. I read these books when I was in 4th and 5th grades. The God Particle by Leon Letterman, Hyperspace by Michio Kaku, and Black Holes by Kip Thorne. So these are the kinds of things that really got me interested in science in the first place. So but what is science, right? The basic principles of science. We always throw around the scientific method, but as a phrase. But I worry that sometimes using the phrase, "Oh, that doesn't follow the scientific method," is misused to bludgeon one's critics in the scientific community. And there are huge misunderstandings as to what the scientific method means, and everyone adds their additional layer to it when the basics are very simple. You test ideas with observations. You refine or reject those ideas, which can't explain the real world. And the 5 basic steps are, as we learn even in elementary school, or make an observation of the world, formulate a testable hypothesis as to the whys or hows of something, run an experiment to test your hypothesis, so your hypothesis should be predictive in some form, analyze your experimental results, what can you conclude? You confirm or refine or reject the hypothesis, and the process starts over and over again. But this is a naive oversimplification, because in reality, sometimes you have exploratory research where you don't even have a hypothesis of what's going to happen. You just want to do something and see what happens. Or you have multiple hypotheses and you're trying to rule some in and rule some out. So this is an oversimplification of what actually happens. And there's also a joke that we should add. There was an article in the satirical newspaper, The Onion. We should add a 6th step to the scientific method, which is seek funding. Because unfortunately, you could have the best idea in the world, but if you don't have the money to test it, if it's an experimental idea and requires equipment or supplies, then it's not going to gain any traction. Mm-hmm. And that is just the sad reality. So the principles of science are an ideal that we strive for, but we don't always achieve them.
If I can just interrupt you, it's technical, but on the live stream we have an alert button that you need to click to hide. If you go back on StreamYard, you should see it on the back, on the lower bottom of your screen. Yeah, that one. That was that one.
There we go.
Perfect.
Okay. So there are additional principles, as I said, beyond the basic ones from slide 4. Confirmation of result. Are results reproducible? Are they repeatable? Multiple trials of the same experiment, as well as new experiments, are useful. There are many examples, including my own field, dark matter discovery claims, that were controversial because they couldn't be replicated. And then what we find when we look back there was that there was an unknown, previously unknown mistake. So controls are very helpful. Purposeful omission of something. For example, in a drug study, you give one group a placebo pill. But controls are not always easy to craft. Reproducibility is not always possible. For instance, in astronomy, we only have one universe. We don't have multiple Big Bangs, multiple cosmic microwave backgrounds we can study. And so some types of science are more observational than experimental. And we must be cognizant of these differences. Another tool that we use besides control is called blindness or blindedness. This is where experiments or human subject participants are purposefully unaware of something. So in psychological experiments, this is where you don't tell the people what it's about. You lie on purpose because that would mess up the result. Or in the example of my own work in dark matter, what we do is we often run experiments in a way where we don't know the answer until we are done taking all the data. Don't look in the data until you're done taking all the data, so that you're not biased either towards forcing a discovery that isn't there or accidentally missing a discovery by being over conservative. Both directions are extremely bad.
Mm-hmm.
So now, launching now into the specifics of my work on dark matter, I want to give you some historical perspective. There was a Swiss astronomer, Fritz Zwicky. There were some other astronomers, Jan Oort, and several others around the same time as Zwicky. So arguments about who was first. But to me, you know, history is less important than the actual science itself. Nevertheless, history of science cannot be neglected. And so Fritz Zwicky was one of several individuals who, around the 1920s, 30s, that era, discovered that there were galaxy clusters with velocities that didn't make sense. The galaxies were moving so fast that the galaxy clusters should have fallen apart. They should not have been held together gravitationally. And he is credited with coining the term dark matter. But for many decades, this was laughed at as not serious. And that his error bars, you know, too big and his conclusions are faulty, until the work of Vera Rubin, who really revolutionized things in the late 70s, early 80s. She really revolutionized things with her work, looking at galactic rotation curves. So what Vera Rubin did was look at the speed at which stars around centers of galaxies, including our own and other galaxies, what do they look like? And instead of what we expect, which is that the speed should go down, like in our own solar system, Neptune and Pluto are orbiting our sun at much slower speeds than Mercury or Venus. We expected to see the same thing for stars, which are revolving around centers of galaxies. And instead, what Dr. Rubin found with her colleagues was that instead we see an increase or a flattening. So instead of a decrease in speed with distance, we found that stars orbiting centers of galaxies do not behave like planets orbiting stars. And this was quite a surprise because the expectation was that this would fall off as 1 over the square root of the distance. And just like we see from simple Newtonian mechanics, you don't even need relativity for that. And instead, we found this increase in velocity. So in our own galaxy, where we are situated on Earth, going around the sun is going around the center of the galaxy together with the local objects at about 200 kilometers per second. So as a scientist, as you can see, I use metric, which is good, especially if you're a primarily European audience. So I'm going to stick to meters, kilometers, proper units.
That's very true. That's very true.
Yeah. So this is a mystery, and one solution to this mystery, I'm going to explain why is this the better or more favorite solution. One solution to this mystery is the same solution that Fritz Zwicky came up with, which is that there is additional matter that we cannot see. And so basically you have a disk which would look like this, and then you add additional matter. This is called the halo, and then that does match the data. But by itself, that information is not enough. By itself, that's not enough, because how do you know there's additional matter and that we don't just misunderstand gravity? So there's additional corroborative evidence of dark matter's existence. And one of them is this example. So this is an X-ray image. This is a false color image from the Chandra X-ray Observatory. So the blue here is X-ray emitting gas. But what's holding that X-ray emitting gas in place outside of that galaxy? So this is a galaxy here, and these are other galaxies. So this is a galaxy NGC 0507. And so on the left side is the X-ray image, and on the right side is the optical image. And the question is, what's binding those gases in place to make those X-rays? So we have more evidence of invisible matter here gravitating, producing gravity that's holding gas in place here, outside of the main bodies of these galaxies and star clusters in this photograph on the right. So in our own galaxy, to explain our own data, the model or the theory is that we have a flat-like spiral galaxy that's embedded in a spherical or ellipsoidal halo of dark matter, which also explains why we have these globular clusters, the red dots in the diagram, that seem to be orbiting our galaxies off of the plane.
Mm-hmm. So to try to do a summary, by looking at the shape of our galaxy, we can deduce where are spots of gravity that holds everything together.
Correct. Exactly. So we have very careful studies of the gravitational forces in our galaxy as a whole, but also in our local neighborhood. Mm-hmm. And so that's why we're able to model this dark matter halo robustly, because we have measurements of the velocities of numerous stars and star clusters in our galaxy, including in our local neighborhood near our sun, which is labeled right here.
And for a part of my audience, how can a gas in space emit X-rays that are a very high, powerful types of light?
That's an excellent question. So there's different mechanisms for emitting X-rays. So for example, you can have black holes where matter is getting sucked in, and at high speeds will relativistically emit X-rays. So, but this is the space between galaxies, right? So what's going on there? So yeah, that's a very excellent question. We do not yet know all of the sources of high energy particles from space. That is a active area of study of the sources of various types of X-rays, gamma rays, as well as protons and nuclei. So that's an excellent question. I do not have the full answer. So gravitational lensing is another thing we can look at. This is related to the last slide, because we are still also going to talk about those X-ray emitting gases. So we have here gravitational lensing is additional evidence of dark matter. This is one of the reasons we know that dark matter probably exists, and that it's not something like, for example, a misunderstanding of gravity, of Einstein's theory of relativity. So what is gravitational lensing? I need to explain what that is. So gravitational lensing is where light is bent due to mass. So what we learn in school initially is not correct, that light always travels in straight lines. Actually, that's true the vast majority of the time, but not when you have extremely strong gravitational fields. So light can be bent if you have a galaxy cluster of many galaxies. Each of those galaxies is hundreds of billions of stars, and each of those galaxies have a supermassive black hole in the center. So this is dozens, hundreds, or thousands of black holes with hundreds of billions of stars. So that's a lot of gravity. So let's say you're looking at this distant galaxy from Earth, and you have an intervening galaxy cluster. That's going to bend the light. So the light from that distant galaxy gets bent, which distorts the image of that galaxy. So this is a cartoon, and this is an actual example here at the lower left of what this looks like. And so what this allows you to do is to calculate the amount of matter that is causing the distortion of the light. And we have an example of that here on the right. So on the right, this is the famous bullet cluster, so-called bullet cluster image from 2006, where you have visible light. You can see galaxies here. So these spots of light are mostly galaxies, not stars. I mean, you have some local stars in the picture, like here in the image, but most of these splotches of light are galaxies of hundreds of billions of stars. And what you have here is in blue an image of the gravitational lensing map. So that's saying where's the most mass. And then in pink, you have an X-ray map of where are the most hot gases that are emitting X-rays. And none of these match. The optical map does not match the centers of the blue spots. That doesn't match the centers of the two pink areas. And the only reasonable way we've been able to explain this image on the right so far is that we have two clusters of galaxies roughly on the left and right here that collided and are passed through each other. And then what happened was dark matter, which doesn't interact very often, forms these lobes at the edges of the image in blue. But then you have mixing of hot gases producing X-rays in the pink. And so the primary robust way we've been able to explain the data behind this image is that we have extra matter that's not contained within the stars. And this matches with the other data, the other type of data, the like rotation curves we talked about earlier, or curves of stellar revolution. It matches not just qualitatively saying there's dark matter there, but it also matches quantitatively, because it matches the percent level, the estimated percent level of missing matter. Mm-hmm. So this is very powerful, very, very powerful.
And I was checking because I think it was a few weeks ago, there was a study published from Stanford University that suggested to use our own sun, the gravitational lens of our own sun, to make pictures of exoplanets. Mm-hmm. It's an article in space.com by Teresa Plutarova. So it's not theoretical physics. It's something that we can observe and that is real. There is a lensing effect that has no source that we can observe.
Absolutely. So there is a lensing effect where the source isn't strong enough. There isn't enough mass in the galaxy cluster. The bending is too much. It's too much bending. And so one can ask, do we trust general relativity? But we just recently discovered gravitational waves, and they match very well the predictions of relativity. And so it's getting increasingly difficult to explain away these observations and say, oh, we just don't understand gravity. There's no such thing as dark matter. As a good skeptical scientist, I have to be open to that possibility that in a few months or years, we may discover that actually we are not interpreting this data correctly. We must always be open to that possibility. But I think it's getting increasingly less likely with the more we learn to say that, oh, there's no dark matter. It's getting increasingly less probable because of all the good data we have from astronomy and from cosmology.
Mm-hmm. So we are comparing two ways of explaining what we observe. So either it's a new theory of gravity, the Mond theory, modified gravity, that could explain that. But in that specific case, you would have to add lots more to what we know of gravity to explain that specific effect, if I understand well.
Yes, I actually have a slide about that. So yeah, you're anticipating it. Very, very good point. So to the best of my knowledge, and so that I'm not attacked, I want to choose my words very carefully. To the best of my knowledge, I'm not aware of any Mond-like theory that can explain the bullet cluster. I'm pretty sure attempts have been made, but to best of my knowledge, a theory that modifies gravity can do this, can explain page 7, the rotational curves very well. In fact, perhaps even better than dark matter with this fewer number of parameters. But I am very skeptical of their explanations of this, of page 9.
And I find that example very interesting because it goes back to the roots of science with Aristotle. And to discover new science, you have your paradigm, and you need to search for anomalies inside your paradigm that isn't explained by the theories you currently have. Mm-hmm. And by trying to explaining the anomalies, you discover another paradigm hide beside it.
Yes, exactly. Yes. So this is also not the end of the story. There's so much evidence for dark matter. I'm summarizing 8 or 9 different types, or 6 or 7 at least today. These are only the first 2. So if we look at something called the cosmic microwave background, which is that is a very rich topic, and it could deserve its own many hours of discussion. So I'm going to do my best to summarize it in only a few sentences. So the cosmic microwave background, this is the best picture we have of it right now. It's from the European Space Agency, from the Planck collaborations. This is from 2013. And these pixels here, orange and blue, are showing you the cold spots and the hot spots in the cosmic microwave background radiation. What is this radiation? It is, in very simple terms, it is the echo of the Big Bang. It is one of the biggest pieces of evidence we have in favor of the Big Bang theory. And what you can do with the cosmic microwave background is you can study it analytically. So this is a pretty picture and a very important picture, but we can also break it down into what's called the power spectrum. And what this graph shows you are the scales at which there's clumpiness in those pixels. And the clumpiness scales tell you how much matter there is in the universe and how much energy. So thanks to the cosmic microwave background, we're able to create this pie chart, which is called the standard cosmological model, or lambda CDM. And what we find is in black, we have dark energy, 69%. In red, dark matter, which I work on. And so this is what you could say a cosmic detective story. It's the case of the missing matter, as well as the missing energy. What is this 25% dark matter? What is this 69% dark energy? We know even less about that. So this pie chart is robustly underpinned by our cosmological data, not only from the Planck spacecraft, but from other experiments as well. And the neutrinos, photons, and black holes are these tiny percentages here. Very often you will hear claims that dark matter is just black holes. And that is that is a good idea. But the problem is there don't seem to be enough black holes to explain that. I mean, this could still be wrong. Maybe this is black holes and we are grossly underestimating the number of black holes. But so far, it looks like there are not a sufficient number of black holes of sufficient masses in order to explain this big 25% piece. Similarly, there don't seem to be enough neutrinos. There'd have to be heavy neutrinos. And so some of these ideas just don't seem to fit. You'll notice that only 5% of the universe then seems to be actually understood by humans. And that's why I think it's so important that we are humble and that we have humility before nature, because we only understand 5% of the universe. So we really need to have some humility in how we approach science. And this 5% is even worse than you might think. You might think we understand 5%. That you and I are made up. That we constitute the 5% of the universe, and that is false. Because inside that 5%, 3/4 of that 5% is hydrogen. 1/4 of that 5% is helium. Everything else that makes up you and me and all of your audience members and the computers we're sitting on right now, carbon, oxygen, phosphorus, silicon, all of that is the sub 1% dregs of the universe created over billions of years by supernova explosions. So chemistry, all of biology is such a small percentage that we cannot even show it on this pie chart.
I absolutely agree. For me, the CMB was one of the major discoveries of the 21st century. But could you just go a little bit in depth on why it is called dark energy and dark matter? It's not black energy and black matter. What's the name related to?
Yeah, good question. The name is just what people decided. I think dark matter was coined by, I believe the term was coined by Fritz Zwicky. I believe in French it's known as matière noire. I love that term.
It was a bit racist, so we say matière sombre now.
Okay. Oh, I preferred matière noire because it sounds like film noir, the genre, cinema genre. So, but that was originally coined, but not in French, but I think in Schweizerdeutsch by Fritz Zwicky, and I believe he's the one who coined that term. And the reason why dark matter, why dark, why not black? I mean, Fritz Zwicky has been dead for a long time, so we cannot ask him. But I believe part of the reason probably is to distinguish it from black holes, because that already has the word black. And as I show in this pie chart, we don't want to confuse the two, because we don't know if black holes are the same thing as dark matter. They probably aren't. And so to distinguish from black holes, I think that's a good reason to use a slightly different word. Then for dark energy, I believe that that was simply to continue the tradition from dark matter, is to, if we don't understand what something is in science, we just throw the adjective dark on it. So dark matter and dark energy are not related. They might be related, we don't know. They don't seem to be. They seem to have actually opposite effects on the universe, because dark matter has a positive gravitational effect, just like normal matter. It holds the universe together. It creates structure, like you see in the pie chart, those red strands, they represent the structure of galaxies. Dark energy has the opposite effect of dark matter. It has like an anti-gravity-like effect that's pushing the universe apart. There are models that claim that dark matter and dark energy are correlated, but we have no proof or no evidence at all that dark matter and dark energy are related in any way, shape, or form. They probably are unrelated.
Very interesting. And so when I was looking to that subject, and I've been following that subject for 20 years, I was wondering, would that be fairer to call that invisible energy and invisible matter instead of dark? Because when I say dark, sombre, to my students, they picture something that is black, that is grayish. So when there is something, but we can't see it in any spectrum of EM radiations. Would that be a fair definition?
I'm not sure I agree, and the reason is because lots of things are invisible. The wind is invisible, air is invisible. So that term, unfortunately, doesn't work either. Quarks are invisible, right, to the human eye. We need to bang particles together in the LHC to quote unquote see them, but you can't see them, for example, with a microscope. You can see
very good point.
atoms with a microscope, but you cannot see nuclei or quarks with a microscope, right? And so I'm not sure if invisible is the correct term, because there are a great deal of things that are invisible, but they interact electromagnetically, they interact with nuclear forces. So I think in human language, regardless of what language we use, I don't think we have the right terminology.
No, it's a very good point.
Yeah.
So it's would that be fair to say that it's an entire new field of physics that is inside dark matter and dark energy, if it's that different from baryonic matter?
Potentially, we don't know. So we don't know. There could be an entire dark sector of dark matter where there's mirror matter of dark quarks and dark leptons. That's one possibility. Or all of dark matter is one new particle. We don't know. It could be a very rich sector of new discoveries. That's definitely potentially true.
And can you explain where does the CMB come from? What is it, and what does it represent?
Sure. So it comes from about 200, I believe it's 300,000 or 400,000 years after the Big Bang, which was over 13 billion years ago. So it's actually a really long time ago. So it sounds like the CMB came a long time after the Big Bang, but not really. In the grand scheme of things, CMB is almost all the way back to the beginning. And basically, the CMB comes from a moment in time where the universe got cold enough so that neutral atoms could form. As a side effect of that formation of neutral atoms, the photons in the universe became free streaming in time and space. They were no longer constantly knocking into electrons that were trying to get captured by nuclei to form neutral atoms. So as a result, what happened is that the light in the universe, remember, stars did not exist yet at this point. So we're not talking about starlight. We're just talking about the light that the universe was essentially born with, just whatever photons per unit volume the universe had, became free streaming, and as a result they were able to as a result we're able to detect them now from all parts of the sky. And this was one of the first predictions of the Big Bang Theory, and as a result it helped propel the Big Bang Theory as the one that had more evidence than other models of the universe. For example, the idea that the universe is eternal and never had a beginning. So the CMB indicates the universe seems to have had a beginning, because it's a very, the CMB was a prediction of the Big Bang Theory that was able to be measured.
And was the CMB considered as an anomaly when it was discovered, or it was expected inside the model?
It was considered as an anomaly because it was discovered not by astrophysicists. It was discovered by scientists and engineers, but it was discovered by technicians who were trying to work on satellite communication. And at one point, they thought it was bird poop on the antenna. So it was initially considered an anomaly until they talked to their astrophysicist friends and realized this was one of the most important discoveries of the 20th century in the 1960s.
I think it's a very interesting story in the context we are talking
Absolutely.
about. That's why I wanted you to expand on it.
Absolutely. So moving on, there's even more evidence for this model that includes dark matter, but also dark energy, and that's the large-scale structure of the universe, also known as the cosmic web. If you look at the universe, we have this spider web-like structure, and there we can. So this not only tells us there's dark matter, because what happens is, according to our computer models, which do match real data and real measurements very well, is dark matter clumps first. So dark matter interacts only gravitationally or primarily gravitationally, and it forms these clumps. And these clumps will then attract ordinary matter, mostly hydrogen and helium gas. And so then what happens is you have this spider web-like structure, and depending on how strict that structure is, you can even measure the temperature or the energy of the dark matter. Do you have HDM, hot dark matter, or CDM, cold dark matter? And right now, the best observational data that we have from astronomy and cosmology and astrophysics is that we probably have cold dark matter. So what does cold mean? It means non-relativistic. So the example I said earlier, dark matter, our own galaxy, we think is moving a few hundred kilometers per second. So that's fast for a human being in human terms, in terms of cars and airplanes. But in terms of physics, that's considered extremely slow, because it's nowhere near the speed of light. So this is what we mean by hot and cold. And of course, hot and cold, these are arbitrary terms, right? Because the truth could be in between. But the two extremes are hot dark matter. Hot means close to the speed of light. Very light particles moving close to the speed of light. Cold dark matter is the model that says dark matter is made of very heavy particles, if it is particles, right? Very heavy particles, and they're moving very slowly compared to the speed of light. And our current data favors CDM, the cold dark matter model. And what the cold dark matter model predicts is, I have an animation here, upper left, is we're able to model how the universe evolved. And our models do a very good job of explaining the large scale structure that we see in the universe today. So you can see here in the modeling video in the upper left. So dark matter collapses into clumps, which then attract the ordinary matter in the universe, mostly hydrogen and helium, that the universe is born with in the Big Bang in the first few minutes. So in the 1980s, we had trouble with this, because hot dark matter is also more favored, but that would not explain the large scale structure. So hot dark matter, like neutrinos, wouldn't be able to achieve this. And so Vera Rubin wrote an essay actually in the 1980s for a book, one of those books I read that I mentioned earlier, where she said we didn't understand the bubble and void structure. But she said that in the 1980s. Now we do have an understanding. We do understand using dark matter to explain the clumping and dark energy to explain the spacing. That doesn't mean we understand what dark matter or dark energy are. All we did, but this is how science progresses, all we did was push the question to the next level of why. So now we understand why, we think we understand why the cosmic web exists, this picture of the universe that we have based on real data, but we don't. But now the next question is, well, what is dark matter and what is dark energy? So this is an example of real data from the SDSS, the Sloan Digital Sky Survey. You can see this structure. And I always show this to my students. I can't help but notice it looks like the human brain. And I'm not claiming, oh, that means the universe is a giant brain and some kind of mystical aspect of this. On the other hand, I think that we should not ignore coincidences like this, because maybe the clumping in the universe, what if the same mathematics can help explain neurology? What if this is not a coincidence, and maybe this is a hint and will help us explain things about the brain? I want to say that as a scientist, I'm not at all claiming, oh, this proves, the universe is, I don't know, God's brain or something mystical like that. Absolutely not. But we should not discount the possibility that maybe there are similar mathematics that describe this structure and this structure, since they look so similar. We should not ignore these possibilities. I think science needs to be more interdisciplinary.
I agree, because my background is more into biology, and inside we have a lot of commonalities we observe between typical forms on life and geology. You could see types of geology you could swear are living beings, like self-replicating triangles inside a cave that seems to colonize everything, or when land desiccates due to lack of water, you have stripes that appear on the ground that are very reminiscent of the veins you see in leaves in plants, because they all stays inside the same thermodynamics laws. So you find the same patterns each time. So I don't think it's such an extent to seek a relation between the shapes you observe at the scale of the universe and at the scale of cells.
Yeah, another example of that is the Fibonacci spiral. Appears
Yes.
everywhere, biology and astronomy. And I don't think there's necessarily anything supernatural, paranormal, mystical about it. What it tells us is that probably similar mathematical equations govern those processes, which is important. That's important to know because that'll further our knowledge.
Yes.
So I want to address, as I promised you, I have a slide addressing the possibility of modifying gravity. Because one of the criticisms of everything I just showed you is, oh, dark matter is simply the new ether. It's simply something scientists have made up, and it's not really there. We just don't understand the universe or understand our theory of gravity. So I love, there's a comic strip, XKCD, and here's one of my favorite XKCDs. Department of Astrophysics motto: yes, everybody has already had the idea, maybe there's no dark matter. Gravity just works differently on large scales. It sounds good, but doesn't really fit the data. And so every few years, a new version of this comes out.
Yes.
And yeah.
Yes, that's true. That's very true. And I've looked at it for 20 years, and every year or 6 months, I see a new one appear.
And every single time, it's here's my new idea, there's no dark matter. And oftentimes, if you dig very deep, what you find is someone has a new idea that explains one piece of the data.
Yeah.
Not all of the pieces I just showed you. It does remind me, I know of your interest in like my own in UAP, it reminds me how you take a famous UFO case or UAP and you can easily explain one aspect, but you forget the other three. That ruin your hypothesis, your mundane hypothesis. And that happens in dark matter, where every 6 months to a year, there's some grand new theory of modified GR, and then the newspaper articles pick up on it because they're like, ooh, look, controversy. Except it's not controversy. It's good science. We must test the alternatives. We must. I'm not making fun of modern modified gravity. These are valid ideas we must test. But at the same time, it should tell you something that they keep getting re-killed every single time. And so most recently, the Gaia experiment, it was helping to kill Mond again. So here's the prediction for velocities in our galaxy, the component, perpendicular component and the radial component. Red is prediction from a Mond-like theory, blue is from dark matter, and black is the real data. Anyone can look at this and see the black point with its error bars is significantly closer to the blue. I mean, it's kind of ridiculous at this point because I think modified gravity is a zombie. And the more that we kill it, but it keeps rising from the grave over and over and over again. Yeah. And it just seems like there is no, every time we seem to try to explain dark matter by modifying gravity, it's a very exciting idea for a few weeks or a few months or maybe even a couple of years, and then it's destroyed again. And this is just a fact. I'm just stating the facts. Of course, proponents of modified gravity will yell at me. But the thing is, I'm a scientist, and as a scientist, we should not be emotionally tied to our theories. I'm not. I've given you all the evidence for dark matter, but I'm not emotionally tied to it. If tomorrow absolutely incontrovertible evidence comes out there's no dark matter, I'll say, that's great. That's interesting. I'll look at that. So I think we should not be emotionally attached to our theories. So, but is dark matter?
Two things on that.
Yes,
First
please.
is that Mond is fair game. I mean, they can always propose new ideas and the other side dismantle it and prove it's wrong, and both become sturdier. Mond has to become more strengthened to explain other data, and on the other side, black matter explain a new data set, a new anomaly that was covered by Mond. So I think it's fair game. It's the scientific process at a global level. It's different science team gently battling each other to get the new discovery. So it's fair game for me. And the other side, I completely forgot, and I'm absolutely ashamed because it was a very good question.
Maybe it'll come back to you later.
Yeah.
But I also put a joke on my slide. If I had a dime for every time someone had their one right new theory, so TOE stands for theory of everything, I would be rich. Because the thing is that theories are only as good as the data that they're able to explain.
And I got back my question. So in France, we have a sociologist, a PhD in sociology, that worked on the history of science and how scientists work. And he published a work where he showed that there was a disconnect at the time where we invented the first instruments to observe matter. So when our eyes couldn't see, we created microscopes and I forgot the name, to see further and to see smaller. And at that point, there was the theory of science that emerged, where you could discover things just by thinking and deducing data. And on the other side, you have observational science, where you observe reality and try to conclude something. Do you think that the monde and the dark matter have these both sides? Monde is a more intellectual reasoning about how can we, by our own mind, explain something, and dark matter comes from we observe that, what it is. And do you agree with my reasoning that the both sides of monde and dark matter represents this dichotomy between observational science and intellectual science?
I think it's only partially true because I think you need both sciences. And I think it's partially true because there are plenty of dark matter theorists who will use their minds to come up with dark matter models. There are hundreds, thousands of them. And similarly, there are people working on monde-like models that will compare to data all the time, to real data. So I think it's only partially true because there is significant overlap in those approaches.
Perfect.
So, but this is a very good point. So I have a second slide on it. So there are many ideas, especially ideas for practical applications. So this ties in with what we were just saying about, for example, using exotic propulsion techniques for interstellar craft that require modifications to gravity. And there does seem to be some evidence both for dark matter, for and against dark matter, and modified gravity. So dark matter has issues too. And I have a link to a video here that summarizes them by Professor Sabine Hossefelder, where she points out the summary of the pros and cons of dark matter versus modified gravity. Because there are some issues. Dark matter cannot fully explain some rotation curves. It cannot explain some amounts of dwarf galaxies, around galaxies, things like that. And so there are still, despite all the evidence I showed you, there's also counter evidence. So it's a very complicated story. But there are some galaxies that have been discovered that appear to be 100% dark matter or 0%. They're basically all normal matter or they're almost all dark matter. That's very hard, I would say, to explain with modifying gravity. So the discovery in the past few years of galaxies that have normal rotation curves or more extreme ones do seem to, we don't know what caused them, I should say, but they do seem to imply dark matter is stuff. And you can have more of the stuff and you can have less of the stuff. In addition, many theories of modified gravity predict new particles. What are those new particles? Maybe they're dark matter. So again, even if you modify gravity, we come full circle back to the need for there being new stuff, more, dark matter. That's not always the case. And I list the work of Philip Mannheim, Professor Philip Mannheim, University of Connecticut at Storrs, who works on conformal gravity. There are many still attempts to that don't have the word monde in them, but they're monde-like, but they're better than monde because they're modifying GR, not modifying Newton. Because remember, we know that Newtonian mechanics is wrong. Not wrong, but incomplete. So the proper way, if you want to get rid of the dark matter model, is you modify Einstein's theory of general relativity. But then the problem is the modified version of general relativity I've seen would fail to, for example, explain the observation by LIGO of gravitational waves. from black holes merging. So again, even modified GR is running up against problems, not in dark matter in that case, but it runs up against LIGO. So the problem is, again, is that nature does not care about my opinion or your opinion. Nature is nature. The truth is the truth. Facts don't care about humans' opinions on little planet Earth. So we're trying to get, of course, to the bottom of this mystery.
And you opened the door, so you have to enter it. How does the Newtonian physics fit inside general relativity?
It's an approximation of when you don't have large mass and you're not moving very fast. So if you take Einstein's theory of general relativity, and for example, you calculate what is the gravitational field of planet Earth, the very first term you get in doing a mathematical, rigorous expansion of the Einstein equation is you recover Newton. Mm-hmm. You recover Newton's law of gravity from the 17th century. So, and this is an example actually of how paradigm shifts have been happening more recently in science. And I'm hoping science historians are picking up on this. But for many centuries, scientific revolutions were everything we knew was wrong before, and now we got to start over. More recently, as we develop telescopes and microscopes and computers and spacecraft, instead the paradigm shift has been very different in nature. Instead, the paradigm shift in the more recent centuries has been what we learned before was almost correct, but not quite. And we need now a bigger theory for which the older theory is an approximation. Mm-hmm. So, for example, we're not going to wake up tomorrow and discover general relativity is wrong. It's too late. It's too late to be wrong. If it was wrong, why does your computer work and your phone? Same thing with quantum mechanics. What we will discover is that these models are incomplete. So remember I said we still understand 95% of the universe, but the 5% we do understand, we understand extremely well.
Yes.
So the paradigm shifts now in science are, what we knew before was only partially true. It's more rare for a scientific revolution to be, that was 100% wrong and we got to start over. That, of course, that can still happen. But if you look at scientific history, that's become rarer as our technology has improved. Like you were saying earlier, we are moving away from armchair philosopher more towards almost every crazy idea we have now is testable.
I agree, but it depends also of the field. So in biology, it happens all the time. All the time, we completely rediscover something we completely misunderstood. But in instrumental science, where we have such precise tools about length of time, length of width, weight, it becomes very hard for physicists today to find another theory that could explain all the data that has been gathered by very precise tools. So I think it's a very good point to raise, because a lot of people are sadly miseducated in science, and either trust science, believe in science as a solution for everything, or do not believe at all in science. And science is just the product of human beings that search something. So it's never perfect. But the good point with instrumental science is that you have objectivity in the instruments, and we have very precise instruments. So it's a big step forward compared to even 2 centuries ago. It wasn't that 2 centuries ago. And 2 centuries ago, we have been on Earth for 400,000 years. So it's a very big step that is sadly ignored by many. About the overlapping you referred to previously, is there a scientific study group that tries to mix Mond and dark matter for explaining everything?
Not many. And so that's why I give you one example here of Dr. Sabine Hassenfelder. She's very good. She's got very understandable YouTube videos for the general public, and there are only a few, and I think I will explain why. Because part of the issue is that people fall in love with their one theory or model and refuse to consider other possibilities. And so I think that I would not be surprised if the correct answer is dark matter is real, but it's only part of the explanation. We also have to modify gravity. I would not be surprised at all, especially because we know we have to modify gravity. We have to, because it doesn't include quantum mechanics. It doesn't include quantum effects. GR has nothing to say about quantum, and in fact, it has contradictory explanation for how gravity works. It's contradictory.
And even his creator, Einstein, was very puzzled by quantum effects at large scale. So, and I absolutely agree with your statement. I can't recommend Sabine's work enough. It is very enlightening, very refreshing to a scientist that has a critical point of view on science. And I can't recommend her work enough.
And one point about instrumentation you brought up. Instrumentation, while one can argue they're objective, are still imperfect because you have human beings who calibrate them. You have to calibrate your instruments with control data in order to understand what they're telling you. And in astronomy, it's very hard to get control data when you only have one universe, right? And so we do still have, even with our instruments, they are still not perfect. And I do think that we should not I worry that sometimes, like you said earlier, there are extremes. People who do not believe in science no matter what, even if the evidence is staring them in the face, even if it will kill them in the terms of medicine and biology, to not believe in science. But on the other hand, you also have people on the opposite extreme, unfortunately, who worship science as if science is a god with a capital S, science, when we know science is imperfect and uncertain. That's the point of science, is that when it's wrong, the proper technique is to self-correct. We don't always do it, because science is full of emotional scientists who love their original idea. But the proper way for science to move forward is, if your idea is disproven, let it go. Move on. And that happened with the cosmic microwave background I mentioned earlier. There were scientists, I think the last one died in the year 2002, who to their dying day refused to acknowledge the Big Bang theory was correct, and said instead, no, the universe is eternal, steady state theory is correct. And they kept reinventing and reinterpreting the data. And that's not the proper approach. Proper approach in science is, my theory was disproven. Well, that makes me sad. Time to move on. The incorrect approach is to be emotionally attached to that theory and say, sorry, I'm not listening to any contradictory data. You're all wrong. I'm right. Stop talking to me. That is an emotional response. That is not a logical response. And Spock from Star Trek would be very disappointed.
And I think we have also to note that scientists are humans.
Yeah.
So when you suddenly discover that the theory you worked 30 years of your life is wrong, it takes a tremendous lot of sturdiness to accept it and continue to work. And it can also endanger your livelihood. If you are a very well-known researcher in a field and you are paid for every year by the state for your research, and suddenly your research is proven wrong, you have a tremendous interest in denying that your theory is wrong.
This is known as in psychology as a perverse incentive. So the way science is currently done by humanity, I think it's miraculous we've achieved anything, because science is very poorly constructed, especially in the United States. There's a very perverse incentive in order to get funding is to maintain your ideas are correct. Now, part of what fixes that, it's not a perfect solution, but there is still the salary that you get from tenure. So once you have tenure and you can't get fired, that's great, because then you can pursue crazy ideas. However, what you just said is still partially true, because the way, I cannot speak for Europe or other countries and other continents, but in the United States, at most institutions, especially academic institutions at schools, you're paid for 9 months as a professor, and for 3 months you're on your own. You either work for free, or if you have funding, for example, from the government, then you can fill in the gap of your summer salary. That's what it's literally called, a summer salary. So it's not a perfect solution, but that at least helps a little bit with what you were saying.
No, that's the reason why our scientists go to the US. We have 30,000 young French scientists that are in the US to benefit from that system.
From that system, yeah. Right. So yeah, moving on though, I haven't told you, completely new topic. Well, not completely new, still dark matter on slide 15. But what is it? So do we have any idea what dark matter could be? We do have several ideas. One is the idea is called supersymmetry in particle physics. This is the idea where for every fermion there is a boson, for every boson there's a fermion. So I know then the obvious question is, what's a boson, what's a fermion? These are particles that spin a different way. We're not talking about literal spin, even though that's what it seems like mathematically, but we're not talking about a literal spin, because particles might not have, they might not be cute balls like in this cartoon. They might not, they're probably not spherical, maybe they're points, or maybe, if string theory is correct, they are strings. But I'm not talking about a literal spin, but nevertheless, the word spin is a good analogy. So for particles that spin one way, and I don't mean like left versus right hand, that's not what I mean. I mean the amount of spin. So if particles were spinning, again, that's an imperfect analogy. We're talking, a very crude analogy is thinking of the amount of spin, the speed. And so the idea here is that for particles that spin have one amount of spin, they have shadow or mirror particles that will spin a different amount. And this is analogous to antimatter, where for every positively charged particle you have negatively charged, for every negative you have positive. So antimatter is an excellent analogy for this. But the big difference is we know what antimatter is. We've been playing with it from the 1930s. We've already discovered it. It's not hypothetical. Meanwhile, there is unfortunately no evidence yet for supersymmetry. It's a beautiful model, but there's no evidence for it yet.
We have to say that symmetry is really important on the physics, because it's something you find pretty much everywhere. Yeah, in almost every big law, you have a kind of symmetry that appears. And what you said was perfectly right with antimatter. And there is a belief, I think, it's my point of view, among physicists, that they try to force a symmetry to explain something that they don't have answers yet.
That is sometimes true. You're right. Sometimes there are probably, I don't think I would say that it would be a stereotype to call every physicist does that. I don't do that.
Yes.
But you're right that there is a tendency among many, that I will grant you, of many, to really look for symmetry. But part of the reason that drives that is, I think, again, you're saying scientists are humans, and in human nature, right? Symmetry is beautiful to us.
Yes.
That may be evolutionary. So there may be a scientific explanation for that. So you're absolutely right. But the difference with supersymmetry is that it's a broken symmetry, actually. It's not a perfect symmetry. Like antimatter is a good symmetry in the sense that the particles of antiparticles and particles have the same mass. They just have opposite electric charge. But in supersymmetry, it's a broken symmetry, to explain why, we haven't found the supersymmetric particles yet. They are much heavier in mass. In this cartoon, it's shown as size, but that's, just a cartoon. We're talking about mass. So supersymmetric particles are not identical in mass. They're much heavier, which makes it more difficult to discover them, more difficult to create them in a particle collider, for example. So supersymmetry is actually a broken symmetry. And the idea behind one side effect of supersymmetry, it's only a side effect. Supersymmetry is not a dark matter model. However, supersymmetry might explain dark matter, because maybe one of these heavier particles may be the lightest of these heavier particles. If it is stable, or stable for billions of years, it could be dark matter. So the elegance of supersymmetry in this case is not in the symmetry, it's in killing two birds with one stone, as the expression goes, is that supersymmetry may explain some mysteries in particle physics, while at the same time explain the cosmological mystery of dark matter. But it's not the only idea. And honestly, it's not my favorite, because I'm getting kind of disappointed at the lack of evidence for it. I mean,
to go further on that, earlier you talked about the possibility that dark matter could be an entire new realm of particles.
Yes.
Could there be molecular dark matter? Could there be solids of dark matter? Would that be just floating very heavy particles?
We don't know the answer to that. That's an excellent question. There is a model called SIDM, self-interacting dark matter. The thing is that we don't know. The only evidence we have is that dark matter interacts gravitationally. Well, we don't know if it interacts non-gravitationally? Does it have its own forces? We know from cosmological data, dark matter does not interact electromagnetically and most likely does not react through the nuclear forces, but it could a very, very little bit. But that doesn't stop the possibility of dark forces. There could be an entire dark sector, and that could be attractive and repulsive dark forces. We do not know. So right now it does appear unlikely, and it seems like dark matter would just be, it could form amorphous clumps, but it looks unlikely that you would have an entire dark matter chemistry with dark matter molecules. But what does unlikely mean, right? That's just our current human opinion, scientific opinion, but it's still a human opinion. So it's entirely possible that there's a rich dark sector out there that has its own dark forces.
And would one of your detectors could differentiate between floating individual particles and a solid interacting with it?
Probably not. I think we would have to build bigger and better detectors for that. We'd probably have to think harder on that. I think that we would need to, if we made a discovery now, like with the current experiments I work on, that would motivate more research and time to develop better ideas in order to distinguish between the different models.
Okay.
So speaking of different models, here's another one, extra dimensions. So one possibility is that there are extra dimensions out there beyond X, Y, Z, or length, width, height. And to explain why we haven't discovered them yet, maybe they're rolled up, have a cylindrical geometry or something on a microscopic level. And a quantum mechanical consequence of an extra dimension like that, such as in the Kaluza-Klein approach, is that you would have extra particles. So that's how extra dimensions explain dark matter, is that if you have a cylindrical a repeating geometry of some sort of extra dimension, that as a consequence of that, it would create a whole sector of new particles, just like supersymmetry. And so again, we have dark matter candidates. Another possibility is that dark matter is just ordinary matter in that direction that we can't see, in that extra dimension. So there are a lot of rich possibilities there.
I will try to summarize, and please correct me if I'm wrong. We are limited by three dimensions of space and one dimension of time in our understanding for our brain.
Correct.
But if we draw a graphic, we can have 2 dimensions represented on the flat surfaces. You can add the illusion of a third dimension by the depth and the line inside. You can say that you only have 2 dimensions, you ignore the third, and the third you already draw is a fourth. So you can create a coordinate system that add a new dimension of space. But you can picture it, it's just a representation on a mathematical, intellectual side. Would that be fair?
Yes, it is. So a great example of this is take a dot and you could turn it into a line. So we go from 0 to 1 dimensional. Now take that line and make a square. We go from 1 to 2 dimensional. Now, if you take that square, you can come up, you can make a cross of 6 squares, fold it up like a box, like a deconstructed box, fold it up and you can make a cube. Now imagine you have a cross, it's called a tesseract, of 8 cubes. You can fold that up and make a 4-dimensional cube. You and I cannot do that. Computers can, and mathematically we cannot picture what that would look like. And so there could be extra spatial dimensions, and string theory as well as supersymmetry, which is a subset within string theory, they're not the same thing. They predict extra dimensions, extra spatial dimensions.
But in my understanding, the additional spatial dimensions of string theory are condensed, very small dimensions. They are not an entire dimension of space that we just can't interact with.
They're very compressed, like in my diagram here. So in this example diagram, I try to explain what does it mean for a dimension to be compressed, because it's very hard to visualize what does that mean.
Yes, that's the problem we have.
Yeah, so here's a cartoon that illustrates what that compression means. Imagine you're looking at a garden hose sitting in your garden. And from far away, the garden hose looks one-dimensional. It's just a line. But if you go closer, you see that the line has some thickness. So it's two-dimensional. But then if you go really, really close, you see, oh, no, you were mistaken. It's three-dimensional. It is a cylinder. It has length, width, and height. It's a rolled up two-dimensional surface in the third dimension. And similarly, extra dimensions might be rolled up on the scale, on sub-microscopic scale, smaller than the scale of atoms. And that would explain why, for example, we don't see these extra dimensions. Why do we only see three? It doesn't mean that the fourth and fifth dimension don't exist. It simply means that they're rolled up on some microscopic level. So this is, but as a good theory, remember, good theory makes predictions, because if they're rolled up on a microscopic level, you can say, well, then we'll never test them, right? It's an untestable theory, so it's not scientific. But that's not true, because this model of a cylindrical extra dimension does predict new particles that could be dark matter or could be discovered, for example, in the Large Hadron Collider in Switzerland. So this is a good model because it makes predictions, so we can prove it or disprove it.
So you are perfectly on time. That's just perfect. 2 days ago in Le Monde, the largest newspaper in France, and very conservative, very somber newspaper, was an article about science and the failure of the CERN, the Large Hadron Collider, to really find anything. They confirmed that the Higgs boson existed, but since then, nothing happened. And all the discoveries that have been made since then were statistical errors due to the level of sigma they were using in the analysis. So would that disprove string theory, or we are not yet at the end of the power level we require to test string theory?
That's a great question. The thing is that the Large Hadron Collider, which is a wonderful experiment, my understanding is that in certain ways it was not as powerful as the superconducting super collider that was canceled in the United States. So there is very good motivation to go to higher energies to keep looking. It's absolutely disappointing that all we found was the Higgs boson, which was a very important, necessary discovery.
Yes.
But the thing is that yes, it is a great sadness that nothing else was found. However, that doesn't mean that supersymmetry or Kaluza-Klein is wrong. We did not invest enough. Even as expensive as the Large Hadron Collider was, is still not good enough. Unfortunately, politicians hear that and don't understand. They're like, oh, scientists will always say they need more money, and don't understand that that is the truth, is that the LHC was just not good enough. It was not our fault that nature put these particles out of the reach of the LHC if they exist. Now, the one can ask the question, though, and this is a very valid question, but is it worth building another collider? I don't want to get into that, of course, because I have good friends who want to build a new collider. But I'm definitely sympathetic to the opinion that, but again, I'm biased, that we could build more dark matter experiments because they're cheaper. But the thing is that I hate to say that, because then I will be attacked by my friends colleagues who work on the collider experiments, which is just a fact. They are orders of magnitude more expensive than my dark matter experiments that I work on. And that doesn't mean they're less valuable. It just means that they're harder to justify. So these somber articles, they do have some justification, but I do think we have to be very careful, because the LIGO experiment was very expensive and it took them, years to build it, and yet they made the discovery eventually. So I think that the problem is that in science, sometimes patience is required. Sometimes a theory is wrong and you will find nothing. But sometimes the theory is correct and you have to be patient. And it's very hard to know the difference between those two scenarios.
I have friends everywhere, to be honest. So I have also enemies everywhere, because I always piss somebody in the audience. But to just make a picture, the price of the LHC is around the same price of a nuclear aircraft carrier for the US Navy. So it seems expensive, but the US have a lot of aircraft carriers.
Yes.
So you need to balance the priorities in the spending. And it's a huge problem for us in France, because we are very far from your level of fundings anyway, compared to the US. But at one point, the potential of mastering dark matter and dark energy is tremendous. I mean, it's an entire new field of physics. Whatever the solution is, would that be MOND, a new zombie MOND, or a new type of dark energy and dark matter, it would be a tremendous discovery to know what it is.
Absolutely.
And yes, it's one less aircraft carrier. Do you need a 60th aircraft carrier in your fleet? It's a question. It's a question.
Excellent point. Excellent question. And I have a very controversial opinion that will make a lot of people angry. I do support, obviously, the defense of the United States. I am very patriotic, and we need a military because there'll always be bad actors. That's my opinion. But at the same time, the scientific part of my brain says it is very angering to me when a fraction of the cost of that aircraft carrier probably would have helped us discover dark matter by now. I tell my colleagues, if we had even 0.1% of the US Defense Department budget, we'd probably have like dark matter powered spaceships by now. I mean, I'm half joking, of course, but seriously, we would have.
No, it's true. That's true. It has been 40 years now, so.
Yeah, and then people laugh, you haven't discovered dark matter, it's taking so long. Why is it taking so long? Because we don't have the money to build the ultimate experiment. We're forced to do it in stages because we're giving tiny amounts of money. And it's like, here you go. Here's a little bit of money. And I mean, some of my criticism is unfair because as scientists, we do have to build the experiment slowly. We do have to stage them forward. We can't just build a 20-ton experiment right off the bat. But the thing is, unfortunately, some of what I just said is true, that if we had money, we could build multiple ton scale experiments for dark matter and really get to the bottom of this mystery faster. So part of the reason, it's not the full reason, part of the reason we haven't found dark matter is because the government would rather spend money on missiles and jets and things that kill people rather than spend money on advancing human knowledge forward. And that's a fact. That's just a fact.
That's very true. That's very true.
Yeah.
And I use the LHC comparison, but people have to picture that that's one of the most costly experiments that were ever devised in the history of mankind.
Yes.
And it's a fraction of the military budget of the single US. You have, after that, you have China, Russia, multiple countries on Earth that could build their own very easily if they decided to.
Exactly. Well, China is considering it. They're considering building an international collider, and I think that's it's a wonderful idea. Science does not care about human countries and human rivalries, right? Nature doesn't care. We should work together to find the truth. So I don't care whether this collider was in Texas or it's in Switzerland or in China. We just need to find the truth and stop bickering. So I that's a very good point. But let me move on to my next. I have a few more slides. We've gone through most of them. I just have a few more slides to go through. I don't have time to talk about axions. It's a different model of dark matter, but we really don't have time to get into it. I'm going to move on to detection strategies. How do we try to find dark matter? And this is good because this is connected to what we were just talking about. Notice here is the LHC. I'm mentioning it on the slide right here. So perfect connection. So there are three different ways we look for dark matter. There's more than three. Like these are the three main ways, but within each of these ways, there's one or two or even a couple dozen different techniques. So one is called direct production. That's what we do at the LHC, for example, at the ATLAS experiment or the CMS experiment. I mentioned ATLAS because I had colleagues at my institution, UAlbany, that used to work on ATLAS. And so direct production is where you take a standard model particle, SM, like a proton at the LHC, you bang it into a second standard model particle, and then you produce new particles. And the reason you can do that is because of E equals mc squared. If you bang particles together at very high energy, that energy can be converted into matter to make new particles. And so that's one of the ways we look for not just dark matter, but anything new, right? That's how we found the Higgs boson. We created some Higgs bosons inside the LHC on purpose. So the reason why you're able to do that is because you take energy, you borrow energy, and you turn that energy into matter. And the reason why that works is because of E equals mc squared. E can be converted into M can be converted into E. M can be converted into E. You see that in nuclear weapons or nuclear power plants, a peaceful use. So you can go either direction, energy into matter, matter and energy. So in the LHC, we take matter at high energy, smash it together, and try to create new particles. So this is the Greek letter chi that looks like an X, and DM stands for dark matter. Another approach is astronomy. This is different, though, from the astronomy I was talking about earlier. It's different. This is not astrophysics or cosmology. This is a different approach. Is you look for dark matter in the sky, where dark matter interacts with itself. And this ties in with your earlier question: does dark matter interact with itself? Maybe it does. One example of that is dark matter interacting with anti-dark matter. Dark matter probably has antiparticles, just like ordinary matter. We have protons, antiprotons. You could have dark matter comes together with anti-dark matter, turns into energy here in the center of the diagram, and then that energy is converted into known particles like neutrinos, gamma rays. And so experiments like Fermi-LAT and IceCube in Antarctica, Fermi-LAT is a spacecraft, and IceCube is in Antarctica under the ice. These are different techniques for doing what's called indirect observation. So that's where you look for the byproducts of dark matter destroying itself by meeting up with anti-dark matter. For example, in the center of the galaxy, maybe in the center of the sun, places where you have a center of gravity, a lot of mass, maybe dark matter collects there. Maybe dark matter and anti-dark matter collect there, and maybe they interact with each other. So that's one possible way. But the way that I work on is circled here in red. That's called direct detection. In that approach, we are waiting for dark matter to bump into an atom inside of our detector. So it's a very different approach than direct production or indirect observation. That's where we're basically waiting for dark matter to interact with the nucleus or an electron. But in most dark matter models that explain the most data, dark matter would preferentially interact with the nucleus. That doesn't mean that has to be the way, but that seems to be the most robust current theoretical understanding, is that dark matter would come in and bump into a nucleus.
As dark matter is clumped together inside pockets of dark matter, would that be possible to propel a probe inside a pocket of dark matter and check a statistical aberration that could appear on a detector?
I think that's possible, but that'd probably be a very expensive experiment, because I think at the level of our own solar system, I don't think we have evidence of significant clumping. I think it's extremely far away. We do have, from the Gaia experiment I mentioned earlier, we have measurements of dark matter clumps and clumping in the local neighborhood, local stars. We don't have the technology to go that far. Right. I mean, our furthest spacecraft that humanity has created, right, that has sent out is Voyager, right? It left the solar system, and it took decades to do it. And it's going tens of thousands of kilometers per hour. So I think that you have a very good idea, but we don't have the technology to do that yet. I think that's a good
I'm
idea.
talking about it because I followed also for the last 15 years the Starshot initiatives,
Yes.
where you propel a very small probe with a laser beam.
Yes.
At almost relativistic speeds. But I was wondering, do we know the speed dark matter moves?
Yes. It's co-rotating with everything else gravitationally nearby. So, for example, near us, dark matter moves approximately at 200 kilometers per second, 220 on average. But that's only an average. Right? Because, of course, there will be outliers. We're not sure about the distribution, but the simplest approximation we can make is that dark matter is Maxwellian. So basically, it's like a gas. There will be faster particles, there will be slower. So the number I just gave you is only an average. Only an approximate.
Okay. Thank you.
So how do we find that? So it's moving around hundreds of kilometers an hour. So the technology that I work on uses liquid xenon detectors. Why liquid xenon? Is because liquid xenon has a beautiful benefit of producing light when particles interact with it. So, for example, if a neutron or a gamma ray or a beta interacts with liquid xenon, it produces a flash of light. And the idea is just to look for extra flashes of light beyond what we would expect from ordinary background radiation. You cannot do an experiment like this on the surface, though. So here's a picture of myself with one of my former postdocs, and before that postdoc, he was a graduate student, of course, Jeremy Mock. And this is us standing in front of the Lux experiment. This is an outdated photo, though. I do need to update my talk because now we have the LZ experiment, which is a bigger, better version of Lux. And we're a mile underground, nearly a mile. Let's see, I need to translate that into kilometers, right? So
1.6 kilometers.
Yeah, that's how far we are underground. But I think it's more like 1.5. We're not quite a mile underground. I think we're about 1.5 kilometers underground. And why are we underground when dark matter is in space? Of course, I always get that question. And this is because it's very difficult to search for dark matter on the surface of the Earth because you're constantly bombarded by other naturally occurring cosmic radiation. So we're people who aren't scientists are afraid of the word radiation and don't realize that constantly we are bombarded. You don't have to go in an airplane, just sitting on the surface of the Earth. We are constantly bombarded by natural radiation. We've got mostly muons, but we have gammas and neutrons and protons and electrons are constantly, pions and kaons and all these more exotic particle types are constantly flowing through us. And so we cannot do a dark matter experiment on the surface of the Earth. In the 1980s, the first dark matter experiments were done in the basement. But then, as we didn't find dark matter, we realized we needed to do a better job. And so now we go underground to mines and things like that. So this was a former gold mine in South Dakota. So that's why we go underground. And the idea is that dark matter, if it is interacting very rarely, the assumption we are making, the implicit assumption, is that dark matter will interact so rarely that it can pass through the 1.5 kilometers of rock and hit our detector. But then you might ask, well, what's special about our detector? Does it attract dark matter? No. The idea is simply you have to be patient. And if dark matter interacts very rarely in the rock, yes, it will also, unfortunately, interact very rarely in the liquid xenon. So there's nothing special about the element of xenon in terms of attracting dark matter, something like that. The idea is that you just have to be patient. You have to build a very large detector and wait an extremely long time. And if you don't find anything, you build a bigger detector. But again, a bigger detector is a very, very tiny fraction of the cost of an aircraft carrier. It's also a very, very, very tiny fraction of the cost of something like the LHC. So even the new generation experiment, LZ, much bigger than Lux, is still a tiny, tiny fraction of the cost of experiments like the LHC. So, but we're currently moving into the ton scale regime of detectors. The experiment I'm working on right now, which superseded Lux, is a 10-ton scale liquid xenon experiment in order to increase the probability of dark matter interacting. Simply mathematically, by giving the dark matter a bigger target, more possible atoms it could bump into.
And still, compared to the cosmological scale we are talking about when we talk about dark matter, it's still a very small piece of our planet that is what will be covered by that 10-ton folder of liquid.
If we had more funding, right, and if we actually cared about funding science, we'd have more dark matter experiments. In fact, a few years ago, the US had a down select where it killed off the vast majority of dark matter experiments. And it decided to only fund 2 or 3. Like there's mine, there's also Super CDMS, there's also ADMX for axions. Now that's slowly changing. There was a new proposal from DOE, but again, from hundreds of proposals, or dozens at least, they only pick 1 or 2 to give money to, because there's no money. Right, because we don't have the money, in the U.S. even anymore. We had the pandemic, and then helping Ukraine, and so there's just not enough money. But you're absolutely right. If we had money and we actually cared about doing science, we would have hundreds of these experiments around the world. We do have multiple, but I don't think we have enough, right, to do the job properly.
I absolutely agree. Agree.
There are a lot of competing experiments. I say that on my slide. That's good. That is a healthy competition. I mean, everyone wants to get the Nobel Prize first, but it's good to have competing experiments. We don't have enough money, though, to have as many, I think, as we need. So
and you need reproducibility of your experiments. Yes, you need confirmation by other studies. There was quite a drama last year. There was a background check made on sociological publications by peer-reviewed journals, and 30% of papers had to be retracted due to bias because there was no confirmation of
Yes.
the data that was provided.
Yes, yes. And what people always forget is that you need confirmation. This happens in biology, happens in medicine, where so many false things are published. It's not just physics. Every field is hurt by this. And it's very sad because, but I have to explain that the right approach is not to never make a mistake. That's impossible. We are human beings. The problem is journals need to allow reproducibility studies. So the problem is that in physics, we don't have this problem. We have thousands of studies reproducing, finding no dark matter yet. And when I talk to my friends in psychology, biology, they were horrified. They were like, wait, you have thousands of papers published with null results and they're all reproducibility? I'm like, yes, it's called science. What are you doing in your field? And yeah, yes. I know.
Yeah, that's exactly that. That's exactly
and
that.
I was horrified. Did you know I learned that in many medical fields and in psychology and biology, reproduction studies are not only, they're forbidden by the laws of the journal? I was horrified. I was like, are you guys doing science? Yes. You're not doing science then. The purpose of science is what Richard Feynman said. The purpose of good science is to prove yourself wrong as fast as possible. And then, only then, if you can't prove yourself wrong, then you're right. That is good science. And unfortunately, I'm horrified by the fact that, for example, there was a study claiming that vaccines cause autism. And the journal would not allow the study that disproved that to be published because the journal said, I'm sorry, we don't publish replication studies because they're not original. And I wanted to throw up when I heard that. I was like, I hope that hopefully people like that will soon retire or die of old age. That's my hope, is that scientists who think that way will slowly retire and die of old age so that a new generation can take over who are not so stupid, who actually apply the scientific method as they're taught in elementary school. And the scientific method includes reproducibility. And so if my current experiment, for example, LZ, if we claim to discover dark matter, we will all want someone to come reproduce it. And if they can't, our result is probably wrong. That already happened in the dark matter field. There's an Italian experiment called DAMA that almost nobody believes anymore, because nobody can replicate their claim of discovery of dark matter. And instead of admitting that they're probably wrong, those on DAMA keep fighting and saying, nope, oh, you're all stupid, and we're right, and you're all wrong. That's not science. That's emotion. That is
exactly.
not.
Exactly. I'm very glad we have this talk so the audience can understand the human side of science. And it will never be perfect. And we have to fight through each layer to progress. And it's a really hard work. It's not just being in an office and writing papers.
And also, and nobody's perfect. I make mistakes in my scientific career, but when the point is not to make mistakes, the point is to admit when you have and fix it. That's good science. So the problem with the 30% that you were telling me earlier is not that 30% were retracted. That's not the problem. The problem is that most journals still don't retract and will pretend it's all correct and fine. That's not okay. That's not okay. It's okay to make a mistake. It's not okay to pretend your mistake never happened or claim it's not a mistake when it clearly was. So that's the issue. So I'm actually shocked it's 30%. I've heard much higher numbers than that. And the thing is, but that's okay, because remember, we should not worship science as a god that is 100% right all the time. That's how people are taught in school that science is. That's not correct. Science is about curiosity and exploration. Science is not about always being right. Science is about striving for that goal, but you often fall short of that goal. You're not always right. But let me explain to you now how the principle of my detector works very briefly, because I know we've been going for a while now. I will explain very briefly the principle. This animation shows the principle behind the experiment I'm currently working on, LZ, and the experiment that came before it, LUX, L-U-X. So the idea is you have a giant battery, basically an electric field. You have an anode and a cathode grid, and you have photomultiplier tubes which can detect even single photons of light. And the principle here is that a particle, like a dark matter particle, comes in, hits the xenon, produces a flash of light, from excited atoms, but it also ionizes in addition to exciting atoms. And those electrons that come from ionization are drifted by the electric field up, and then you get a second flash of light. The reason for the two flashes of light is so that you can reconstruct the position and the energy of the interaction more effectively. So that you can, for example, rule out dark matter versus a particle we already know. And so that's why there are two flashes of light. It helps with differentiating different types of interactions.
Does each particle have a very specific signature?
Yes, but it's not perfect. It's not specific enough. And so you still have to do a statistical analysis because, for example, an electron interaction may look like a neutron interaction or a dark matter interaction. Not always. On average, they are different and have a unique signature in different amounts in those two pulses. But there is a statistical overlap. And so we have to be very careful on that. So there is separation, but it's not a perfect distinction between signal and background.
So even if you have a result, you will need several statistical analysis of your results to be sure that it is right.
Yes, exactly. Yes. All right, so what do the results look like from running an experiment like that? It looks like the final result of an experiment like that is a graph like this, where you exclude some parameter space. So the y-axis here is the strength of interaction of dark matter, and the x-axis is the mass of dark matter, because we don't know what the mass of one dark matter particle is. And so it's a range of statistical possibilities. And so every experiment will draw a line, like this orange line that says experiment A, this blue line says experiment B, this green line says experiment C. And so then you have theoretical models like supersymmetry, and they will be a blob shape on this graph, and potential signals like the Italian experiment Dama Libra. You have potential claims of observation of dark matter. They would also be a blob on this graph. And so if somebody passes your blob, it makes it with a line, it makes it unlikely that your result was correct. Not impossible, because what if you use a different type of atom, use a different type of molecule, xenon versus argon, different technologies. So it does not conclusively show, but it does make it more probable that you made a mistake if someone else's experiment passes by your circle and doesn't find anything. So right now, the status is we do not have a conclusive discovery that the community agrees upon. We have claims of discovery, but we don't have a conclusive, unambiguous thing that's been confirmed by multiple experiments or multiple types of detection. So right now, what we have is these lines are getting lower and lower and lower. You'll notice the line is not flat. It's not a flat line on the y-axis. It's not just a horizontal line. And the reason is because if dark matter is very light, it's not going to produce enough energy to see in your experiment, and so it curls upward. At high masses, it also curls up, because if dark matter is very heavy, then it has a very low number density in our solar system, in our galaxy overall, and then we'll never see it. And so that's why statistically what happens is that the experiments curl up, both at low mass and both at high mass. So if dark matter is very heavy, it's going to be very, very hard to find. If it's very light, it's going to be very, very hard to find. But if it's in this sweet spot, and the sweet spot is about 10 to 100 times the mass of a proton, if dark matter has a mass in that range, then it has a good chance of being found, perhaps even in the next 10 to 20 years. So there are new ideas for experiments to do low mass and some to do the higher masses. So it's not impossible if it's very low or very high. We just need to be smarter about designing our experiments. So this is a cartoon in the upper left, but in the lower right, this is a more a real example. These are previous, so these is supersymmetric models here. These are previous experiments, and then this is a projection here of where we're going to go this year with the new experiment I'm working on, LZ, that just turned on this year. Or last year rather. So I keep forgetting it's 2022. And the idea behind LZ is to go, several orders of magnitude lower in the possible interaction rate of dark matter. And you see this orange section here, this is known as the neutrino fog or the neutrino floor. This is where your dark matter experiment becomes so big that now it becomes a neutrino experiment, which is both a good thing and a bad thing. right? One person's signal is another's background. So what happens in this orange region here is that if your curve starts getting lower and lower and lower down here, like where this red dash is now neutrinos in your detector might unfortunately overwhelm any potential dark matter signal. And so at that point, it gets much more difficult, not impossible, but much more difficult to make progress in this field.
But wouldn't neutrino detectors have a noise background due to WIMPs if that would happen to be in that scale?
That's a possibility. And that's why some of the newer and neutrino experiments like DUNE and MicroBoon are actually considering, they're developing new analyses and people looking at ways of going the other direction. So it's definitely a possibility.
Mm-hmm. Oh, that's very interesting.
Yeah, so right now we're pushing down. That's what this giant arrow is. We're pushing down by running longer and building bigger detectors. But we're also pushing to the left by running detectors with lower energy threshold. What could you do with dark matter? We don't know. It's just new knowledge for the sake of knowledge initially. I have this crazy idea, maybe because there's so much of it everywhere, right? 25% of the galaxy and the universe. Maybe we could use this as some sort of fuel. But the thing is, how would you use it as a fuel if it doesn't interact with itself? Very often, at least, like you wouldn't have any sort of chemical interactions. Nevertheless, and how would you collect it if it has zero electric charge, like in the default model? It's difficult. It's very difficult. Very difficult to say what you could do with it. So this again has to do with what we were talking about earlier. There is such a thing as science for the sake of science, just for the sake of new knowledge. But then there's also practical applications of science is a separate issue. So, for example, when electricity was first discovered, it was just pure science, right? No practical applications. And now electricity runs our lives. And the same thing might happen with dark matter. In a few centuries, we might be unable to let go of dark matter like currently we're unable to let go of electricity. It runs our lives. So I think we just lack the imagination currently. Especially because we don't know what dark matter is. We currently lack the imagination to even really speculate robustly on what dark matter could actually do for us. Yeah, so dark energy, and I have a joke here from Star Wars, the Force lightning from an evil Sith, that's Count Dooku from episode 2. And dark energy is the name we've given to our ignorance. It's not necessarily related to dark matter. It is the fact that we have discovered, and there was a Nobel Prize for this, is that our universe, the size of our universe, the scale rather of our universe, appears to have an exponential increase starting. And there appears to be an acceleration phase of the universe, where if we project to the future, it looks like the universe will probably expand forever and have either a big freeze, a big chill, or a big rip. And so the dark energy is just a name given to our ignorance of what is this something that caused the universe to accelerate in expansion. How did we discover dark energy? It's very different from dark matter. So for dark matter, we do have cosmological evidence. We also have cosmological evidence for dark energy, but most of the cosmological energy for dark matter is a different approach. So the approach is to look at something called type 1a supernovas, which are distant stars that exploded. A typical type 1a supernova might be like a white dwarf and a red giant star, but there could be other ways to create these types of explosions. And the idea is that if the chemistry, the astrophysics and the chemistry behind this explosion is identical, or at least very similar, it gives you what's called a standard candle, where it should always be the same brightness and the same relationship of the brightness as a function of time. And so basically, we can look at distant supernova explosions, and if the dimmer they are, that tells us the farther away they are, and that gives us a standard candle of brightness that allows us to calculate distances of very distant objects. So because these supernovas are very bright, they can outshine entire galaxies. Dark energy in itself is extremely exciting because depending on the nature of what dark energy exactly is, and if we could find a way to harness it, I have YouTube links here to a discussion of how dark energy could maybe someday potentially be used for things like a faster than light travel, like a Star Trek style warp drive, or even for time travel to the past. But those are, of course, very crazy, very, very, very speculative ideas. But I threw them in there because I think that I think it's okay to speculate in science. I'm not claiming that those are confirmed things, but I think it's fun. It's fun to speculate sometimes on the crazier ideas. We are centuries away from those potential things because we don't even know what the heck dark energy is. But I felt I would throw those possibilities out there. So dark energy, what is it? Why would it be useful for some crazy ideas? The dark energy might be, again, we don't know for sure because we don't know what it is. One idea is that dark energy is related to something called zero-point energy or vacuum energy. It seems like it might be the same thing, but we cannot say for certain. We don't know what dark energy is. So dark energy might be related to what's called particle-antiparticle creation. So in even a so-called perfect vacuum, you will have creation of particle-antiparticle pairs. So there will be like electrons and anti-electrons, protons, antiprotons that zip in and out of existence. And this sounds like a crazy idea, but it's a consequence of quantum mechanics, of quantum field theory, and we can measure the effects. So the classic example of this is called the Casimir effect, which, to the best of my knowledge, was demonstrated conclusively in the laboratory in the 1990s. And this is where you have a parallel plates that will develop a very slight attractive force, where there's less force in between the plates, more on the outside, and you have a very slight attractive force between the plates that's created by virtual particle and particle pairs. But there is a controversy, and this has to do with ontology of information in science. Are virtual particles, quote unquote, real, or are they simply a mathematical tool? We can see their effects, like the Casimir plate, or in the case of the hydrogen atom, it creates or any atom. The existence of virtual particles create a very small shift in the energy level. So we know this so-called quantum zero-point energy. We know its effects are real. But the question is, are the virtual particles themselves something, quote unquote, real that we can harness and use? So the side effect of these virtual particles on cosmological scale, so this is a pair of plates in a laboratory, right? So what's happening on cosmological scales is that these, for very complicated mathematical reasons, these particles have an anti-gravity-like effect. It's not the same thing as anti-gravity. That's why I'm very careful in my wording. It's an anti-gravity-like effect on cosmic scales that's pushing the universe apart. But again, this is just one possibility because we don't actually know what dark energy is. This is currently our best guess, though, is that this is what dark energy is.
It's a perfect opportunity to ask. In 1977, the Japan in France was created. One of the first scientists that worked on it was called Claude Power, and he was hired by the CNRS, National Center for Research in France, and he left the CNRS because they refused to fund his research on anti-gravity. And I find it really weird that something that could have so much technological potential as anti-gravity didn't receive any funding in itself. And okay, it's an high-risk research because you are not sure of finding something. So for an administrator that has to validate credits line of research, it's a risk. But any science is a risk in itself. So I think I saw the same thing in the US, where anti-gravity research began in the 40s to 60s and then disappeared from the field.
Yes.
And now we hear a lot about how dark energy is a form of anti-gravity effect at galactic scales. So we have a kind of observational proof that something like it exists in the universe now.
We do.
And we still have no research on it from what I saw.
That's an excellent point. And the reason for that is we no longer take risks on things that are probably wrong, but if they're right, are of immense benefit to humanity. We never take those risks anymore. That includes in the United States. In fact, with ideas that are even probably right is not good enough. So I've had many proposals rejected on new ways of looking for dark matter. And I was told, stupid idea, too risky, it'll never work. And it's literally 0.0001% of the Defense Department budget, for example. It's absolutely absurd. And this happens all the time, and it's getting worse as the US runs out of money. For example, we spend money on everything but science. And I think that the problem is only going to get worse before it gets better, if it ever gets better. So the thing is that there's no such thing anymore as high risk, high return research. They will claim it exists, like NSF, National Science Foundation, will pay lip service to it publicly and say, oh, absolutely, we have this program, that program to fund high risk, high return. But then you actually submit a proposal and your proposal gets rejected. And you,
okay, I'm sorry, I have to interrupt, but you said the sentence. So we just had a conference from NASA saying that they were funding a new research group to study UAPs. And the only sentence that really rings to me, that's, I don't remember, one of the three said, it was a high risk, high interest research. And the description was connecting to other agencies and asking what that data they had. And it was really weird to me.
But that actually proves my point. Because actually, if you look more carefully at that, you'll see they gave it almost no money. They gave it $100,000, which sounds like a lot of money, except it's not in research. $100,000, well, if I got $100,000, that's actually less than the amount of research funding I have. That's not enough money for, maybe I could have like one student and a little bit of salary for me, and then there's nothing left for equipment. So like $100,000 when it comes to research is kind of a joke. It's kind of it's pennies, because once you tack on the overhead and the fringe benefits, health insurance. Remember, in the US, we don't have free health insurance for everybody. Once you add the health insurance for the student and the professor, and you add the overhead rate for the university take its cut, that amount of money is laughable. It's a joke. $100,000 is nothing. So that actually, the NASA study proves my point, actually, exactly. Is we pretend we fund high risk, high reward research, but we give it a teeny tiny bit of money. And then everyone acts surprised when the study fails because you didn't give it enough money to succeed. It's not always the case that the theories are wrong. You didn't give them enough money to succeed.
And there was a very interesting piece of epistemology showing how the science influence among politicians decayed over time after World War II. Because with Oppenheimer, the science was at its maximum. Everybody believed that nuclear bomb on Japan won the World War II, dismissing what the USSR did at the time. And he was one of the major influence of the deciders inside the US for the next decade, and then fell from grace. So starting there, when I look at the scientific research, I see a great decay of ambition in discovery starting there. Do you have that same feeling?
Yes, I think we don't have the ambition anymore to make big discoveries. We would rather develop, actually, we do still have funding for science if it's weapons. So we do still have that. So we are very excited about finding new weapons with which to kill each other. I don't understand why you even need new weapons when we already have nuclear weapons, and so we already have the trump card. But instead, what we've done the past few decades, which, I mean, what sociologist would have ever predicted this, right? Einstein did not predict this, and a scientist didn't. Instead, we pretend nuclear weapons don't exist, and we just continue to fight each other with machine guns. It's astounding to me that humanity did that. Like, we created the ultimate weapon. And then instead of saying, okay, now we have the ultimate weapon, we must never go to war again. Instead, what happened is we will pretend atomic bombs don't exist, and we will continue to fight each other with machine guns and regular explosives. It's just, Einstein never predicted that. Oppenheimer never predicted that. They predicted World War II was the war to end all wars because of the discovery of nuclear weapons. And instead, what happened was something very different, unfortunately. Human nature took over, and we decided, no, we love war. We love war and killing each other so much, we will pretend atomic weapons don't exist, and we will continue to fight. It's crazy, absolutely crazy. Instead of world peace, after World War II, we just continue to kill each other and just make threats with nuclear weapons like Putin did, but no one actually wants to use them, right? No one wants to be the first. And that's the situation we're in. But we will continue to fund better defensive and offensive weapon systems, even though we already have the ultimate weapon. It's very strange to me. And we'll continue to fund Russia, China, and the US all continue to fund bigger and better weapons, non-nuclear, conventional ones. Meantime, there's so much science to be discovered that could help humanity, that could, for example, get us interstellar spacecraft and propulsion. And yet we give those kinds of ideas very, very tiny amounts of money. Or we'll fund them, but it'll be classified. It'll be funded through, Department of Defense, and then we don't hear anything about it. And then 30 years from now, we'll eventually get it, but then we don't have enough scientists working on it right now.
So I had the exact same reasoning, and I was wondering, okay, so maybe in the 60s, the anti-gravity research disappeared from public research and went into the military. And I asked around, and there is nothing. Since Frank Milburn published his work for the Bazat Center in Israel, explaining how tic-tac technologies could revolutionize small states, but with a very high capacity in technologies like Israel. I was expecting states like the UK, like France, like Israel, with like Germany, with very high scientific research, industrial capabilities, but lack of primary sources to jump on that technology. And it's complete silence, both on the military research and public research. So I'm really wondering what is happening. No, but it's like everybody is blind to what is happening right now.
Yes, and again, it's because if an idea is risky, then nobody wants to fund it, because many of those anti-gravity ideas, they are risky in the sense that they don't have a full-fledged theory that shows they will probably work. But the thing is that we will never make brand new discoveries if we don't take some risks. Well, let me wrap up. I have only 2 more slides. There is some funded research, but it's not for practical applications. That doesn't mean you won't have practical applications hundreds of years from now. There are tabletop tests of dark energy, in particular connected to what's called chameleon, the chameleon hypothesis, that dark energy is a particle. It's not some mysterious field, but similar to dark matter, it's discretized as particles. So there are scientific results, there's published results on nothing has been found yet, but that doesn't mean that we won't. And I was really excited because I started making connections, very controversial, obviously, with my friends and colleagues. I started to see some connections with some of the work that is allegedly being done by Hal Puthoff and others on alleged UAP crash parts. I was like, this sounds very similar in terms of the materials that are needed for these studies. There might be some sort of tenuous connection, I thought. So it definitely made me very, very excited. So there are tabletop tests of dark energy that are moving forward, that are trying to test whether dark matter is a particle. And if it is, maybe we can study it in the lab and not just with a telescope. So I'm very excited about these kinds of studies because they take dark energy out from the telescope and down to the lab. So just like with dark matter, you have both the telescope and astronomy, and you have laboratory, which I think is a very nice approach to have both. So I'm going to conclude. So in conclusion, 95+% of the universe is unknown. Absolutely cannot claim we understand everything, or even almost everything. On the dark matter side, at least, experiments are ruling out a lot of possibilities. I like to speculate because there's so much dark energy and dark matter. Could we harness them in some way, utilize them? And I think good examples of that are like electricity, that I mentioned earlier, that electricity at one point, there is a story, I don't know if it's apocryphal, that in the UK, that allegedly the king or queen of England visited Michael Faraday's lab and asked, what is electricity? And allegedly Michael Faraday responded, I don't know, Your Highness, but whatever it is, you will be taxing it one day. And
that's a very good point.
Yeah, and it's the same thing with antimatter. Antimatter was once only hypothetical. Then we found it in the lab. It was hypothetical in the 1920s. Then we found it in the 1930s in cosmic rays. And nowadays, you are injected with a very safe, very small amount of antimatter for medical use. For example, PET scans, positron emission tomography, to study cancer, not to cure cancer, but to find where it is, find where the tumors are.
Yes.
So just like electricity and just like antimatter, maybe dark matter will have an application. Who would have dreamed in 1930 that antimatter would be used to diagnose cancer? Nobody thought of that in 1930. Similarly, there are probably applications of dark matter that I've never thought of, and that will come long after I'm dead. So by definition, dark matter doesn't interact with light. That's one of the reasons why it's called dark. So it doesn't interact electromagnetically. But there could be exceptions. We talked about naturally occurring clumps that come from gravitational clumping. And so with that, I will conclude. And I'm happy to answer any more questions.
Oh, you have 2 hours in front of you. So, no, firstly, thank you so much for that presentation. It was a real pleasure to talk to you. So it was really, really interesting. So I looked into the history of dark matter too, and found Fritz Zwicky. And what I found very interesting was why was he disregarded at the time? And it was because among the works he did, there was some very strange works for the time. And among them, there was that discovery of dark matter. So when other scientists looked into that discovery, it was tainted by the other works they knew was wrong. So it was considered wrong. So I found that very human, that one of the biggest discovery of our time was disregarded due to other research that tainted the reputation of the scientist. Do you, how important is the reputation of scientists in science?
Very, and I think that's wrong. That's a bad idea, and I'll explain why for several reasons. Great, that's a really good question. The reputation should not be used to protect people who are wrong, right? That's a logical fallacy. It's called right argument by authority. Oh, Albert Einstein said this, and Richard Feynman said that. So they are human beings. They could also be wrong. So Einstein, for example, is a good example. He was great, but even he made several calculations which were wrong because he's a human being. So I think reputation is over exaggerated, and this can be harmful. So, for example, worship of Einstein, an example I just gave, might prevent people over worship of Einstein, might prevent people from modifying the general relativity in ways that are necessary. And another example is I'm at the University of Albany in New York. I'm not at Harvard or Yale or Princeton. And so when I try to publish a paper, there is absolutely bias against me, and people who claim otherwise are either lying or they're deluded and they don't understand reality. If I had after my name comma Harvard, I could publish all kinds of nonsense, and I can prove this to you. This is going to anger many of your listeners, I'm sure, but it's just a fact of life, and many people have noticed this. I'm actually one of the lucky ones because I'm white and male. If you are a woman or an underrepresented minority in the United States, and you also are not at Harvard or Yale, then you have a double hit. Then you're not going to get your research published. Well, you will, but it's going to be much harder. So unfortunately, reputation is part of this system, and there are ways of getting rid of it, but nobody wants to do them. There are some suggestions out there from sociologists of science suggesting, why don't we use double-blind peer review, where, for example, the author and the reviewer don't know who each other are, instead of one-sided blind review. This is not a perfect solution, because in my field, we are in large collaborations. Everyone knows who's on the LZ experiment. So it's not a perfect solution, but it will help individual people who are trying to write a publication by their own, and they have no co-authors, and so there's no way of finding out who they are. But even then, with Google, you find out who they are. But I think that that reputation is oversold and overused, because it goes both ways. Someone with a good reputation can be wrong, and someone with a bad reputation or no reputation at all at a small school might make the next big scientific discovery, but they will be ignored because they are not at one of the major schools or labs.
Mm-hmm. So we've concluded almost at the seconds the time that we are allowed to conclude this talk. And again, I loved it. Could you please introduce UAPX and how can people contribute to the funding of your scientific experiments inside it? For quick recall, last January, my audience overwhelmingly chose UAPX as his science research team of the year. So all fundings coming to me are directed towards UAPX. So can you please explain what is the work you're doing with UAPX and what is your plan ahead?
Sure, I'll be so happy to tell you all about it. So UAPX is an organization that was co-founded by Gary Varese and Kevin Day, who are former Navy members who are of the U.S. Navy, who are trying to find the truth on their experiences as they were directly involved. They were not the pilots, but they were on the ship. They were directly involved with the famous or infamous 2004 Nimitz encounter, which was covered in the 2017 New York Times article, which kind of changed the culture and changed the conversation about UAP. My colleague, Professor Kevin Knuth, is vice president of UAPX and head of science, and he is the one who recruited me. So he was recruited by Kevin and or Gary. I don't know, because that was before. I don't recall, it was before my time. But then Kevin recruited me, and because we need real scientists to be looking at this problem of UAP, and so, but the thing is that we can't fund it with government funding. There's no government funding for this. There is for private, secret, classified work on it. But unlike my field of work in dark matter, we don't have there's no program I can apply to for UAP, right? There's no official funding mechanism like Department of Energy has, National Science Foundation. So UAPX is a nonprofit organization and relies on donations in order to buy better equipment than we had on our first, expedition, to have better cameras to be able to try to move the study of UAPs forward past just having, we all have this, the one blurry image of the one anomalous object, but we want to move the science forward on UAP by having multiple images from different angles, having multiple modalities. And we were already partially quite successful with that with our first expedition. But the thing is, we need more expeditions to other UAP hotspots, and we need money for that. So it's not just the equipment, but also to pay for travel, because the thing is there are different locations around the country and around the world that are allegedly hotspots of UAP activity. So we don't want to just deploy cameras randomly anywhere. That's useful too. But we also want to focus our efforts. We want to, for example, not just test other locations, but we also want to someday have the money necessary to go back to Laguna Beach and Catalina Island. Because remember, science is about reproducibility. We want to reproduce that mysterious hole that we found in the sky that we can't explain, away as a camera glitch. But what if it is a camera glitch? We need to reproduce it. So reproducibility is the hallmark of good science. And unfortunately, that's really hard in UAP studies, right? Oh, you see the one object at one time, you don't see it again. But that's why our focus on UAPX, right, the X stands for expedition, is instead of studying historical UFO cases, there are plenty of organizations that do that, and they must exist and are worthwhile. For example, Kevin and I also belong to the SCU, the Scientific Coalition of UAP Studies in the United States, so which also I think has international membership as well. And I think that there are already organizations that study historical cases. UAPX's approach is orthogonal, is perpendicular to that approach. It's a complementary approach where our focus is get our own data, where we know what camera was taken with, we know who took the pictures, we have custody of the data, we have provenance of the data. And so that is the approach that UAPX had years ago, even before it went public. That was the vision of Gary and Kevin Day.
So I have a very high respect for that, for your research team, because I come from biology, and we love to have a boot on the ground and to look for new species and discover things. And it's something that is very usual for us. And when we talk at somebody who's trying to do tabletop experiments to prove something, we are glad that we just have to go on the next field next to his lab and discover a new species of beetle that is just there and that completely was ignored by the rest of the earth. And we also know the cost of it is that on the ground, the instruments just fail you every time. And it's a basic rule of observational science. It fails all the time. And it was so cute when I saw you doing the experiments and saying, oh, shit, it doesn't work. Oh, shit, it doesn't. And yes, that's observational science for you. You need to have 4 backups to have a possibility of recording something. And I have an immense respect for scientists to choose to go out of their labs and do ground experiments to try to discover something.
You're exactly right. So you see this happened. Yeah, this absolutely happened to us. So a good example of that is the main event we have of a mysterious dark spot in the camera. We have all these stupid arguments now of whether it's a camera glitch or dust on the lens. None of those arguments would be happening if the FLIR, if the infrared cameras hadn't gone down, and the power hadn't failed on them at that exact moment, at that time. And so these are great examples. Initially, of course, we tried to, we connected that to, it's part of the phenomenon that equipment fails. And then it turned out it had a boring explanation of that it wasn't mysterious why the equipment failed. But the thing is then we are attacked by our critics on UAPX of, oh, look, it's garbage, your equipment failed. But we're just honest, because equipment does fail. And
yes, and all the time on the ground it fails all the time.
But now we are going to design a much better experiment next time. We had a battery backup, but we didn't have enough batteries. Next time we're going to have a battery backup on each camera instead of just one. We learned very valuable lessons that we can now go back and improve on what we did. But the data we took, we were shocked, because we expected to find nothing. We were so happy that we might have found 1 or 2 or even 3 potentially very anomalous and interesting events. We were not expecting to be that lucky. We were expecting to find nothing because, we figured UAP are very rare. Why would we get so lucky? So we were very pleased that we were able to see what could potentially be interesting events.
Matthew, thank you very much for this talk. Thank you, everyone, for following that show with Professor Matthew Szydagis. And we'll see you each other at the next episode.
See ya. Bye. Thank you for this time.